finish the conversion factors, all these calculations, and hopefully start to talk about matter and energy. And we mainly have a few things to talk about, basically how you use these approaches with the conversion factors to calculating. You all pretty familiar with that already from the labs that we've done, so it shouldn't be an issue. So you will need to calculate percentages, and we will be calculating percentages quite often. To calculate percentage, you may notice that two numbers should have same units. So you can calculate percentage of, body fat in a human body. If you measure 18 kilogram body fat in a 100 kilogram patient, the percentage of body fat will be 18%. Does that make sense? And vice versa, you have to be able to calculate units based on the percentage conversion factor. Okay? So for instance, if I tell you that the percentage of fat in milk is 3%, then my question would be, how much fat are in 100 grams of milk? Think, okay, 3% means that it's 300th, okay? Does that make sense? So the conversion factor is 3 per 100, okay? So in 100 grams, it will be 3 grams. Does that make sense? Now, what if, let's talk about it a little bit more. What if you have another question? For instance, you have a class of 20 people. And no way it reminds this class, I didn't count. 20 people. And I tell you that out of these 20 people, 7 are females. What percent of females you have in that class? Well, you have to divide 7 by 20 first, right? Mm-hmm. But it doesn't give you the true percentage, because what you really have to do, you have to divide 7, the fraction that you're looking at, over total number of students, 20, and then multiply this result by 100 to get the percentage. So if you divide 7 by 20, you get 0.35. You multiply it by 100, you get 35%. Does that make sense? I don't think percentages will be a problem for you. So I will try on the exam that's going to be on Monday, I will try to give you the calculations that do not involve multiple conversions or anything like that. I checked recently, they're going to be quite straightforward, okay? So you won't have to, convert milliliters to liters and then liters to percent, okay? I don't really care that much about math. I care more about you understanding how the conversion works, okay? However, we may need to use these multi-step problems. We may need to use conversion factors when we solve multi-step problems. So in order to solve the problem, it's a key to write down what you have and what you need to find. It's really important. Like, I'm not kidding. If you can do it in here and give me the answer, well, good for you. But the more complex the problem is, the harder it is to do it. Okay? So it's really critical to write down what you know and what you need to find. So step 1 is you figure out what's given and figure out what's needed. Then you figure out what you need to do. Okay? Then you write down conversion factors and or equalities. When we're talking conversion factors, for instance, if during one step you need to convert kilograms to pounds, you need to write a conversion factor, which is 2.2 pounds in 1 kilo. Equality is if you get the answer, intermediate answer in kilograms, and the question is grams, you need to write an equality, right? 1,000 grams is 1 kilogram, so on and so forth. Okay? And then you calculate the answer. Calculations are entirely up to you. You can do the entire problem using no numbers, just letters or any names for your variables, and then do one gigantic formula at the end. Or you can do intermediate results, calculate step by step. So for instance, here, that's a simple problem. We have a person who weighs 164 pounds. You need to calculate the body mass in kilograms. So what do you need to do? You need to write, you given a mass in pounds, you need a mass in kilograms. So you need a conversion factor of pounds to kilograms, right? So what should be at the bottom? Pounds. At the top, in the numerator, you should have kilograms, right? So here's your conversion factor. 220 pounds per kilo. Okay? That's another one, kilos per pound. You want to use the second one to cancel pounds out. Okay? So you have 164 multiplied by 1 divided by 220. When you do calculations like this, you need to know the number of significant figures. Okay, here you have 3 significant figures in the first and 3 significant figures in the second in the conversion factor. So based on the rules of multiplication for significant figures, you have to write the result with the least number of significant figures. You don't have any least, you just have 3. So your result would include 3 significant figures, which is going to be 74.5. I don't really know what the actual result on the calculator will be, but it's probably going to contain more numbers than that. Does that make sense? Now, what if you need to use 2 conversion factors? Well, use them step by step. Okay? So you look what you have, which units you have. So look where you're going to get, and you try to figure out how to get there using the conversion factors that you need. Okay? So let's say we've got the prescription for 0.150 milligrams of a drug. Okay? Milligrams. That's important that it's milli. That's the dose that the patient should take. We're clear. However, 1 pill contains 75 micrograms. Okay? So how do you do that? First, you need to convert 75 micrograms in the corresponding number of milligrams. And then, when you know how many milligrams in 1 pill, you can figure out how many pills you need. Does that make sense?
Yeah.
So, what you would do? You would take milligrams, right? And you need to convert 150 milligrams in a microgram. So how many micrograms are 1,000 micrograms in 1 milligram? Does that make sense?
Mm-hmm.
So what's the dosage? Dosage is 150 micrograms. Sorry, it's terrible to write anything. Circling is fine, but writing is a pain. Okay? So the dosage that patient is prescribed is 150. How many micrograms 1 pill contains? 75. So we'll erase this whole thing. And we will write this, that you have 150. I'm going to skip micrograms just for the sake of writing. You have to multiply 150 by the conversion factors of micrograms per pill. Micrograms should be at the bottom, 75. Number of pills, 75 micrograms per pill at the top. Micrograms. Cancel. 150 over 75 gives you 2. So you have to give a patient 2 pills. Each of them contains 75 micrograms. Does that make sense? Yes. Good. Now the last thing that we're going to discuss today is density. It kind of falls into the category similar to concentrations. And I find sometimes that this concept starts to be confusing. What you need to divide by what you need to multiply by what to find mass or volume, density. So what is density? I'm going to skip. I'm going to go back. It's all recorded. Density is the mass of a substance that occupies a certain volume of a substance. Does that make sense to you? Now I want to stop for, not stop, like I want to take pause for a second and become as visual as possible. We will learn, or you already know, that all substances consist of atoms or molecules. Does that make sense to you? Right?
Sorry, can you say
all substances consist of atoms or molecules.
Yes.
Okay? Yes, we're good, right? So imagine you have some solid substance, say iron. It has certain density, and it means that there is a certain number of atoms in the certain volume that this iron takes. Does that make sense? If you will increase the volume, the number of atoms, like if you take a bigger chunk, it will occupy the bigger volume, but it will also contain more atoms. So density doesn't really change. Does that make sense?
Yes.
Let's say you melt the iron. The atoms that used to be packed really, really tight start to be packed loose. So the density of liquid iron will be less than the density of solid iron. Does that make sense? Because same number of atoms, you take this chunk, you melt it, and it starts to occupy that much of a volume. That makes sense? So density will decrease. Then you jack up the temperature unbelievably high, and you start to evaporate iron. You can do that, okay? Now, vapors, as any gases, you know, they will occupy whatever volume you will give to those vapors. So the volume will increase dramatically, but same number of atoms is going to occupy that volume. So density of the gas will be even less than the density of the liquid. Does it make sense?
Yes.
This rule, sort of, you know, common sense idea that solid of certain substance is denser than liquid and liquid is denser than vapors is generally true, with some exceptions, of which the most notable is water. Ice, which is solid water, is actually not as dense as the liquid water.
You mean the ice is less dense than
the
water?
ice will float, right? Because it's not as dense as liquid water. That makes sense?
Yeah.
Because think about this. What would happen to all those poor fishes if ice would be denser than water? Ice would sink and squish them. That's really one of the features, among others, features of water that practically enables life on Earth. It's kind of unique. There are explanations to that, but that's kind of an important idea. But in general, solid has the highest density, liquid has lower, and gas has the lowest. Does that make sense? Okay? So how do we measure density? What are the units? We can measure it gram per cubic centimeter, okay, or gram per liter, or gram per milliliter. Doesn't really matter. You can use whatever units you prefer. For gases, usually, gram per cubic centimeter or gram per milliliter is just inconvenient because the unit becomes really, the number becomes really, really small. Just inconvenient to use. So we usually switch to gram per liter. Does that make sense? Now, why do we care about density? What's the importance? Well, first, it allows us to predict whether something is going to float in a certain liquid. All right? So, let me give you, so water has density of 1 gram per milliliter. Which means that ice, with its density of 0.92, as far as I can see, I never can remember that, okay, it's less dense than water, and it's going to float in the water. That makes sense here? Mm-hmm. Quark, yeah. Now let me ask you this. Imagine that you have a liquid, say gasoline, which has a density of approximately 0.85 gram per mil. If you very carefully pour gasoline over water, what's going to happen? It's going to float, right? It's not going to sink. Does that make sense? On the other hand, if you will take another liquid, such as mercury, with a density of 13.6 grams per milliliter, okay, and it will pour in the water, what's going to happen? It's going to sink. This is how mercury, like pure mercury, is collected and stored in a chemical lab. It's never stored just in the bottle, because the vapor is toxic. It is stored underwater. They don't react, they don't mix, it's at the bottom, very convenient. You can actually take a sample without taking any water with it. Really convenient. And the vapors are trapped inside. Does that make sense to you? So first, we figured that objects that are denser than water would sink in it, less dense will float. And that applies to any liquid, really. Okay? For instance, if you will take iron with the density, I want to say 5.6. I'm not sure. I wouldn't take my words to the bank, but let's go with 5.6. And you throw it in the water, which has a density of 1. What's going to happen to that iron rod? Now, if you have a pool of mercury with a density 13.6, and you throw an iron rod in the pool of mercury, what's going to happen to it? It's going to float. That makes sense? If there will be any, I don't remember, yeah, there are some, there are calculations. I believe in the exam I provide all the densities in the exam. So you don't need to memorize. It just gives you kind of an idea, okay? So you look at this, like cork, ice, and wood, they're all going to float in water.
So do we need to memorize all the...
God forbid, no!
Is this table going to be on it or no?
Say again?
Is this table going to be on it?
You will not need it.
So
I mean, it's just to kind of, to kind of marvel at the numbers and look at this and say, wow, gold is really dense. Holy cow. Something like that. I don't really know. Now, here's an interesting thing. Sometimes copper, what if you have gold coins? Okay? Gold coins, pure gold coins. should have a density of 19.3, right? Now, if you add copper, they're going to be lighter. So they basically, what I'm trying to say is, people who made counterfeit money in the olden days, they would add something cheap like copper. The coins would appear to look like gold coins, but a person, like a scientist, could determine the density of the gold coin and say, nah, that's not as dense as an actual gold, so that's counterfeit. Something is added there. Does that make sense? So I see I lied to you about gasoline. I never remember the numbers. We have Google for it. Okay, but gas is much lighter. Ethanol is much lighter. Okay? Olive oil, if you carefully pour it, it's going to stay on top of water. Okay? Now, for us, I'm going to throw a term towards you. We're going to go back to it. It's called specific gravity. Okay? Basically, specific gravity is a ratio between the density of a particular compound versus the density of water, which is conveniently 1 gram per milliliter. Does that make sense to you?
Mm-hmm.
Yes.
Of water, like gram per milliliter of water.
Gram? Great question. Gram per milliliter of volume. Volume is the same no matter what you are measuring. Does that make sense? Let it sink in. Volume doesn't change if it's 1 liter of water or urine or gas.
The same liter.
The volume is the volume. Does that make sense?
Yes.
So,
but the weight.
bingo. The mass of whatever is in that volume can be different. Let's do clinical stuff, okay? So, water, 4 degrees Celsius. Water has the density of 1 gram per cubic centimeter. We're going to refer to it from now on as just 1. We're good? And you have 2 people that they pee in the beaker, okay? And one person was working outside in the heat for 3 hours without drinking anything. And another person just had, 5 beers, okay? How would the urine, in terms of the color, compare between these 2 people? The outdoors guy and the beer drinking, huh? Outdoors will be dark. Mm-hmm. Now, what about density? Which one will be denser? The outdoors guy. Why?
Because it's going to be more concentrated.
Because it's going to contain more chemicals like urea and creatine. Basically, less water, more other stuff. Okay, and we measure specific gravity of urine. Okay, when you go to the doctor and they do your analysis, they measure specific gravity. Okay, and it's variable because, believe me, if you go to a doctor after you worked outside for like 3 hours, specific gravity of the urine will be, pretty high. It's still going to be normal. If you have a kidney failure, the specific gravity will be skyrocketing. Okay? That makes sense. Or if you have a disease called diabetes insipidus, when you cannot hold water, it's going to be quite opposite. Specific gravity will be practically 1. It's going to be much less than this parameter of 1.003. It's even less than that. Almost 1. Does that make sense? So specific gravity can tell you about kidney function and about some endocrine dysfunctions, endocrine problems in the patient. And this is why we care about the concept of specific gravity. For gases, I mean, we use density sometimes, but it's much more evasive because density will greatly depend on the pressure, obviously. You know, if you take air from that room and start blowing into the balloon, the density of the air in the balloon will be much higher than the density of the air in that room. That makes sense? Got it?
No, can you say that one more time?
Okay, so if you take a gas and start to pump it into a closed volume, its density is going to increase. You bring in a box in this room, okay, sealed box. You open it, and the density of the air inside of that box will be the same as the density of air in that room. You connect a pump to the box and start pumping air inside. The pressure will go up, and the density will go up. You will have much more air in that same volume. So density of the gas, we try to kind of avoid that topic as much as we can. Okay. Now, how can we measure a volume? If you measure a volume of, can you measure approximately volume of that phone? How?
Measure.
What would you do? Length times width times height. I mean, it's not going to be very exact, but quite close. That make sense? What if you want to measure my volume? That's hard, isn't it? Like by measures, it's hard.
Do it with a mold somehow.
Much simpler.
You gotta do your math.
Much simpler. Objects displace the same volume of fluid as their volume. So you need to sink me in the water. But you need to sink me in some kind of a gigantic graduated cylinder. Does that make sense? So take a gigantic graduated cylinder and fill it up to, say, 2 cubic meters of water. Okay, you have like a giant cylinder, and the meniscus is at 2 cubic meters. You take me, and you throw me in, and you pull me by the legs, so I'm staying all underwater. What's going to happen to the water? It's going to go up. So you take a measurement of the level after I'm submerged, and you see my volume. That's really convenient if you need to measure a volume of, well, anything that sinks. Okay? Like, you can measure volume of an apple, or a banana, or something else. Okay? You may notice it, when you cook, you have a certain amount of water, you drop an onion in that water, and level goes up. Because onion displaces the volume that is submerged. So, what does that mean? Onion is not going to sink, right? It's going to float. It's going to be partially in. Does that make sense? Yeah. So, the part that will be underwater will displace its volume. The part that's above, no. That makes sense? So, that makes sense? So this is how you can measure volume of like some weird shape, like this metal rod. Okay? So you can take this rod, right, made out of zinc. You throw it in the water. Okay? Initially it was 35.5 milliliters. After you throw it in the water, the volume becomes 45 milliliters. What's the displacement volume? 9.5. So that's the volume of your rod. Does that make sense? Don't measure the volume of your phone this way. That's going to be the last thing. You will have to replace the phone afterwards. Okay? Now, imagine that we have the volume of that zinc object and we have the displacement volume. Okay, so we have mass, 68.6 grams. We have a volume. We can measure density. Have you heard the story of Archimedes? The Greek dude who was famous for screaming Eureka when he sat in the bathtub. He was charged, he was given a task to find out the way how to figure out which money are counterfeit. And he thought, because he didn't know how to. He realized that counterfeit money should have less density, but how to calculate it. And once he sat in the bathtub and the water was displaced by his body, he realized that he can measure volume of money. He can measure the mass of the money. And he can find density of a particular coin. And he can see if the coin is real, like the gold, or if it's counterfeit. That make sense? So he's famous for this, but in my opinion, the coolest thing that he's done were the giant reflective mirrors that he used to focus sunlight on the fleet of the Roman Empire, burning them to the ground. That was awesome. Like gigantic lasers, when lasers were not even known. You're going to have 2 or 3 calculation tasks on the exam. It's multiple choice or multiple choice, but you will have to figure out which answer is right for calculating either density, knowing the volume and the mass, or mass, knowing the volume and the density, or volume, knowing the mass and the density. Am I clear? Let's see what I mean by that. So let's say you have 2 teaspoons of the cough syrup. Teaspoon is quite unconventional unit of what? Volume. Yeah. You see that 1 teaspoon is equivalent to 5 milliliters. Milliliters, it's a volume. Because think about this. 1 teaspoon of cough syrup is going to weigh very different from 1 teaspoon of liquid gold. Okay. So we know that the density of the cough syrup is 1.20 grams per mil. Keep an eye on significant figures. Okay? So now we need to calculate how many grams were taken. So first, we need to convert teaspoon to milliliters, and then milliliters to grams. So this is how we do it. Teaspoons to mils. This is the conversion factor here. So you see 5 mils in 1 teaspoon. You want teaspoons to cancel each other out, so you need this conversion factor. And that's your first equation, first part. 2 teaspoons multiplied by 5 mils per teaspoon. Does that make sense? And then you need to multiply the product of that multiplication by the density of the cough syrup. So mils are going to cancel each other out. So in the end, you have 3 numbers that you have to multiply: 2 by 5 by 1.2. Now, this and this are exact numbers, so you don't really care about teaspoons or mils. All you care in terms of the significant figures are 2, 5, and 1.20. Which number has the least significant figures? 2.0 and 5.0. So it's 2 significant figures. This is your answer. 12 grams. Does that make sense? Before we go any further, let me ask you another question. So here we're using density and volume to find the mass. Now, go to this table so I give you something kind of relevant. Let's say ethanol is 0.8. Okay, you see? 0.8 grams per mil. That's density. Okay. So I am telling you that we have 80 grams of ethanol. What is the volume? So we have 80 grams. So you need to do the conversion factor, right? Does that make sense? The density of ethanol, as we discussed, is 0.8 grams per mil. Can you flip this conversion factor upside down?
1 milliliter.
Yeah, 1 milliliter. Absolutely, that's what you can write. 1 milliliter per 0.8 grams. Does that make sense? So you just flip, density is a conversion factor itself, okay? So you flip density upside down, you multiply 80 by this number here, you cancel grams, and the final volume will be 100 milliliters. Does that make sense? No. Does that make sense? No? No? Okay. Good. Good. Good, good.
Because of the scribbles from me. Yeah.
Because of the scribble?
Yeah.
Hold on a second. We can do something useful here. Boo, boo, boo. I'll do this. Let me do this. Okay. It's a clean sheet. Okay. Again, scribbles are going to be absolutely terrible, but at least I don't have anything else here. All right, follow me. So, density. We're going to call it. Come on. We're going to call it D. Is 0.8. For simplicity, all right? 0.8. Grams per mil. Okay? That's just density. That's point. Okay?
So that gram per milk. Not
Per milliliter.
Oh, per milliliter.
0.8 grams per 1 milliliter. Which means if you take 1 milliliter of ethanol, it's going to weigh 0.8 grams. Does that make sense?
Yes.
That statement that I just made. Good? Okay. So I tell you, I have 80 grams of ethanol. Okay? What is the volume? In order to find volume, you have to have a conversion factor that would have grams at the bottom in the denominator. Yes.
So the 80 grams of ethanol is the mass, right?
It's the mass, yes.
Okay, I'm just not
Absolutely, absolutely. Thank you for asking. Okay, we're good? That's mass. M is mass.
Mm-hmm.
Okay?
So it's,
Go ahead, go ahead.
I don't want to ask a dumb question. But
There are no dumb questions.
So the equation, like how, like D equals M over V, or no?
For density? Yeah.
Okay.
So you can, look, if you can throw away the conversion factors and calculate it as adults using the proper formula for density, which is right here, this is the proper formula for density. You will make me the happiest person in the world. If you can just say, what do we need to find? Volume? Volume will equal mass over density. That's it. We swell. Does that make sense?
Yeah.
Now, if you can do that, good for you. It's going to be much faster, much more reasonable. If you prefer conversion factors, I don't see any problem with that. If you prefer conversion factors, what should you, bless you? You think, okay, bless you, how do I do the conversion factor, bless you, which would have grams at the bottom. So think about this. Density is the conversion factor. It tells you that there is 0.8 grams in 1 milliliter. Does that make sense? This is essentially the same as to say that there is 1 milliliter of volume that 0.8 grams occupy. Got it? Mm-hmm. So these are two basically equivalent conversion factors. So you write down 80 grams multiplied by this conversion factor. Grams are cancelled. You need to divide 80 by 0.8. That will give you 100. That's your 100 milliliter answer. Does that make sense to you here? Got it? Does that make sense? Did you understand what we just calculated, how we calculated? Density is a conversion factor. We're going to do the density lab today, so don't worry, we're going to do plenty of that, flipping up and down. Okay? Good? Now, specific gravity. That's what I told you. Density of a substance versus density of water. Now, specific gravity is not, doesn't have units. Do you understand why? It's a ratio. It's relative. Does that make sense? So if we say that a certain fluid has a specific gravity of 2, it means that it's 2 times denser than water. That makes sense? Since water density is 1 gram per mil, you can say that that density of that fluid will be 2 grams per mil. Okay, what's specific for mercury? The density will be 13.6. What will be the specific gravity of mercury? 13.6 divided by 1, which gives you 13.6. Does that make sense? Yes.
Are we always going to be assuming that the water is at 40 degrees Celsius?
Yes. Definition of the specific gravity is that water has a density of 1. You always compare it to 1. Does that make sense? Are we clear? Any questions about this? Now, a couple more words regarding the homework. Oh, come on. Yes, end of the show. Discard my annotations. Okay, here we are. It's alright. Okay. I have no idea that it's there. Okay, if you go to the course content, and you go to homework assignment. Yeah, it's done. I'm going to add the content. Happens. I'm going to add the content today. And in that homework assignment, you're going to have a lot of tiny little problems. Something like calculate the density, calculate the specific gravity. Which of the following is matter, chemical or not chemical. Does that make sense? So do it. It seems intimidating, but it's much easier than you think. Yes.
It would just do for next class.
It's due Monday, and I insist that you do it before Monday because that will prepare you for the quiz. Okay? Does that make sense? I will put it like when we wrap this thing up. Sometimes I think that I upload stuff, but I actually haven't. Okay? That happens all the time too. So with that said, we're going to start. I will be able to make this work. We're going to start talking about matter, energy, classification of matter and energy, and so on and so forth. So we need to know what is matter, what is energy, and how one can be converted in another. Because, for instance, in clinical settings, different matters, red, milk, it's all matter, can be converted to energy by your cells. So, matter is anything that you can touch, hold, anything that has mass, anything that can occupy space. Your body, is that matter?
Yes.
The ceiling, the light. No. You cannot, yeah. It doesn't occupy any space. This air in this room, does that matter?
Yes.
Absolutely, yes. So things like light, heat will not be a matter. Okay? That make sense? So how can we classify matter? It's kind of branched. And we're going to start with the separation into pure substances, pure substances versus mixtures. So a pure substance will have a defined composition. Say you somehow obtain water that contains only molecules of H2O. Is that pure substance? Yes. Okay. You buy milk. Is milk a pure substance? No, it contains a lot of chemicals. You take water and dissolve sodium chloride in it. Is that a pure substance? Not anymore. That makes sense? So pure substances are quite infrequent, really. But when we're going to be talking about chemical reactions, stuff like that, we're going to imply that we're dealing with pure substances, of course. So mixtures important about them is that they aren't chemically combined. Let me explain what I mean. Imagine that you have coal, which is basically carbon. Okay? To make it more fun, you have diamonds, which is carbon. Like you have a pure diamond, which is carbon. And you decide to show everybody how rich you are, and you decide to burn it in oxygen, which is also a pure substance. When you burn diamond in oxygen, yeah, you can do that. You're going to produce carbon dioxide. Carbon, the diamond, was it a pure substance? Well, if it was good diamond, yeah. Oxygen that you used for burning it, was that a pure substance? Yeah, yeah. Well, if it's not air, if it's oxygen, yeah. If it's good, yeah, it's pure substance. What about CO2 that is produced? It is pure substance. It's carbon dioxide, So this is chemical combination. When you take water and sugar and mix them, that's the physical combination. How do we know? Can you separate water and sugar? Yeah. I mean, it's going to be levers, but you can do that. That make sense? So that's the difference between chemically combined and physically combined. Good? Got it? So pure substance can be further divided into the elements and compounds. And from the chemical standpoint, it's one of the most important distinctions that we can make. All elements consist, and now listen carefully, from only one type of atoms. Can you give me an example of an element?
Helium.
Helium, perfect. Helium is actually a fantastic example because it has indeed atomic structure. It consists of atoms. What else?
Hydrogen.
Hydrogen, sure. Yeah. Iron, oxygen that we just talked about. Diamond. Diamond is an element. Well, carbon is an element. Diamond is one of the forms of a carbon. That makes sense. Now, compound, something that has two elements or more than that. So carbon dioxide that we talked about is a compound. That make sense?
The carbon dioxide that was produced from the oxygen.
Burning of coal in oxygen. Yes. Carbon dioxide is a compound. Water, perfect. Yes, it's a compound. Huh? Salt, sodium chloride, yes. If we talk about pure salt. Because if we talk about sea salt that you buy in a grocery store, as, when you take it out and start it into your food, it's not a compound. It's several compounds physically mixed together. You can separate them. Air, is that a compound?
Yes.
No. It's the mixture of elements and compounds, because oxygen and nitrogen will be elements, carbon dioxide will be compound. I'm not talking about noble gases is also present, but it's the mixture, and you can separate those. You can take air and you can isolate nitrogen from it, oxygen, noble gases, CO2, it all can be separated. Does that make sense? Now, important thing about compound is that atoms are mixed in the same proportion. So when Steve mentioned water will always have the formula H2O. 2 atoms of hydrogen per 1 atom of oxygen. It can't be H3O or HO. No, H2O. Carbon dioxide is always CO2. Does that make sense? So we figured out elements. You're gonna not, so okay, let me also clarify one thing. The quiz on Monday will not contain this material. That makes sense? Will not. So it's chapter 1. I try to give you quizzes on the chapters. Okay?
Chapter 1 and 2. The quiz is chapter 1 and 2.
Chapter 1. Okay. I think I know the confusion. Because in the lectures, the titles are like chapter 1, chapter 2. The first lecture, the first PowerPoint that we finished today, that's your quiz material. Am I clear?
Chapter 1 and 2.
Whatever. I don't care what the chapters are in the book. I present, look, I threw away several chapters that we just cannot fit in the course. Like, scientific method would be lovely to talk about, but we just don't have time. Does that make sense?
Yes.
So, that first lecture that we finished today, that's your material for the quiz. Okay? Got it?
Yes.
Got it? That's it. This first, this 5 slides, forget about it. Well, not forever, but. Compound. Discuss this. Compounds can be extremely simple, like water or hydrogen peroxide. They can be super complicated. Well, not super, but complicated, like sugar. Okay? Does that make sense?
Yes.
But they're all compounds. And they contain 2 different kinds of atoms. 3. They may contain 4, 5, even more kinds of atoms. but important sugar, like table sugar that you buy in the grocery store, will always have chemical formula like this. Okay? Now, table salt, an example, contains sodium and chlorine gas. Now, I really like this statement. The decomposition of sodium chloride produces sodium and chlorine. Good luck with that. Good luck with decomposing salt. I don't think humanity produces enough energy to decompose 1 gram of salt. However, you can technically take sodium, it's soft, very chemically reactive metal, throw it in chlorine gas, and sodium will burn in the chlorine gas, producing sodium chloride. It's totally doable. I mean, it requires engineering, but totally doable. Does that make sense? So you can take element sodium, you can take element chlorine, you can mix them, and they will produce a compound sodium chloride. Does that make sense? It doesn't work all the time. If you would look at the formula of sugar, it contains carbon, hydrogen, and oxygen. If you will mix carbon, hydrogen gas, and oxygen gas, you're going to make an explosion, but you're not going to make sugar. Okay? So, many compounds, you cannot produce them from atoms directly. You have to go through some other steps. Yes?
I just out of curiosity, so are the different kinds of sugar, do they have different chemical, like raw sugar compared to white sugar?
Crap. Basically, white sugar is sugar that, so imagine you have a cane, that's as much as I know about the sugar manufacturing. When folks produce sugar, it's initially syrup, and then they crystallize it. And when you just crystallize it from the syrup, it's brown sugar because of all the contaminants and like crap that comes from cane, and I don't know why it's considered to be healthy. Or, huh?
Doesn't it
Yeah, sure.
slower to metabolize in the body? So
No, not really. No, it's the same sugar. Totally same sugar. So don't lie to yourself. No, same sugar. So the pure, like the white sugar, you take this brown sugar, dissolve it in water, and then recrystallize again, so that in the certain conditions only white sugar will start to grow crystals. That's how you purify a lot of solids. Does that make sense? So basically, if you take sea salt, dissolve it, and then will start to crystallize, like evaporating in the very controlled conditions, you can produce sodium chloride, you can produce sodium bromide, potassium chloride, potassium iodide, all kinds of salts that contain in the seawater. Does that make sense? So it's like terms. When we say sugar here, this formula refers specifically to the sugar called sucrose. For instance, milk sugar, lactose, will have different formula. Okay? Maltose, which you can find in the products like beer, any malt derived products will have third formula. Does that make sense? It's sort of our vernacular that we call it all sugar. Now, mixture. Substances are mixed, physically mixed together. So, water solution of sodium chloride or syrup will be a mixture. Does that make sense? Okay? And that, what we were talking about, substances can be separated. If you mix water and sugar, you can separate it. It's going to be hard, but you can. That make sense? For instance, if you buy vodka, which should contain only alcohol, ethanol, and water, you can almost separate. Okay. You can get almost pure alcohol in water. That makes sense? So you can physically separate. Vodka is the mixture. Butter is a mixture. You can separate different chemical components, different types of molecules, different substances in butter. Okay.
Like the oil.
Oil, okay.
No, I'm talking about like the oil and butter, right?
Butter is a mixture. Oil is not. So, huh?
There is no oil in butter.
Say again?
There's no oil in butter.
No. There's no oil. What I'm saying is, butter contains different kinds of triglycerides, usually oils. Okay, if you buy oil like corn oil, it usually contains only one type of oil. Usually it's a substance. Okay? But if you buy like a mix, like cooking oil, it may contain like corn oil and vegetable oil and canola oil, and they're going to be all mixed together. That's the mixture. And technically you can separate. Okay? Now mixtures can be homogeneous, like syrup, or salty water, or brass, or vodka. And does that make sense? So basically, you don't see the different parts of mixture. Okay? Or I'm going to go back. They can be heterogeneous. In this case, you can see the mixture. That's a pretty crude example when you throw a piece of metal in the water. Of course, as chemists, we're not really interested in a chunk of copper sitting at the bottom of the water-filled glass. What I find more interesting in terms of the heterogeneous mixture is, say, what will happen if you will mix water and oil? Imagine you close the bottle and you start shaking it. Huh? Like really, really vigorously shaking it.
You see a lot of bubbles.
A lot of tiny little droplets of oil floating in water. It's still heterogeneous, but it looks almost like homogeneous mixture. Does that make sense? What's going to happen to that homogeneous mixture over time? Yeah, it's going to separate. So, well, let me ask you this. Have you seen smoke? Like, in the city when it's, I don't know, near some power plants or coal burning stuff, you have this sort of, okay, forget smoke. During the rain, after the rain, you have this water hanging in the air. That's mist, yes. That's heterogeneous mixture. Does that make sense? If you will kind of leave it for a while, the water will condense and fall on the ground. So these mixtures are particularly important for us as clinicians. They're called colloidal mixtures or colloidal solutions. One of the easiest examples is milk. If you leave milk for a while in the fridge, what's going to happen to it, especially if it's really fatty? Separate. Okay. Some colloidal mixtures will separate faster. Some will separate slower. For instance, there's a very particular type of mixture that is used to study properties of colloidal mixtures. If you take gold, and you convert it into very, very fine powder, and you mix it with water. By fine powder, I mean like super fine powder. You won't be able to tell that it's gold. So it is going to be, the speckles will be so small. You can make the colloidal gold. You can dispense it in water, and there are colloidal solutions of gold which are heterogeneous. So there are speckles floating in water, but they will be stable for years. Gold will not precipitate on the bottom. Colloidal chemistry is extremely interesting, extremely complicated. I'm super happy. It was 4th year. I went through this. I bullshitted my way through the whole course. I do not remember anything except for that colloidal gold. Now, mixtures. So these homogeneous mixtures, we gave a lot of examples from like air to well, vodka. But one of the important applications if you're scuba diving, gas mixtures. If you think those fellas that dive underwater breathe air, sometimes they do, but mostly it's a special mix of oxygen and nitrogen and often helium gases. So basically, what happens if you go low and low and low, if you breathe only oxygen, as far as I remember, when you go up, you start to develop a condition in which your blood quite literally starts to boil because of the changes in the pressure. If you breathe in this mixture, it won't. So you can dive like really low. It's people who do professional, like high depth diving. I'm talking about 200 or 170 feet underwater. They will use very sophisticated mixtures. Okay. Does that make sense? Just curious. Now, that kind of gives you a general classification. It's gonna be the last thing. So I love flowcharts. Okay, and I think they allow you to structure the knowledge in a very convenient way. So here you can see, okay, matter, all right, something that is touchable, something that you can handle, not things like light or heat, can be divided into pure substances and mixtures. Pure substances can be elements, one atom, compounds, two or more kinds of atoms. By the way, can you separate atoms in a compound using physical methods? No. That's kind of a definition. In mixtures, you differentiate between two. It can be homogeneous, like syrup or brass or mixtures of gases for diving. Air, that's homogeneous mixture. They can be heterogeneous. Well, like colloidal gold or milk. Does that make sense? I'm going to stop at this point. I'm going to